Now, Boolean functions and truth table. Let's talk a little bit about that. So, Boolean function is like any other algebraic function expressed as a function of list of variables with corresponding equivalent Boolean expression to evaluate the function value. Okay, so for example, an f of x, y, z means, okay, my Boolean function has three Boolean variables, x, y, z means they can take either 1 or 0, this one of these values, and this function is defined in terms of some Boolean expression which says, okay, it is x and not of y or z. Okay, so this is a function, and usually we write it, your precedence of and comes before precedence of or. So it's basically really means x and y not of y. So not basically is the highest precedence here. So it's an complementary form of y. That's what we call in the digital logic complementary form of y. Means if y takes a value of 1, y bar or y tick is 0. If y is 0, y value is 0, so y tick or y bar is called 1. So by the way, so I will talk about this y tick, y bar. I most probably is going to use y bar as a term for negation of some variable. Okay, or y not y but negation of y. So any variable name like a bar is basically not of a, b bar is not of b. Just that's kind of I used to say about this negation term. I call them as a bar. There is nothing wrong with call it as a y tick, a tick, or a y bar, a bar, or not of a, not of b. Any term will do. So I settle down with a term like an a bar, b bar, y bar. So y tick, if I see a symbol, I call it a y bar. Okay, just a convention, just to make sure you guys understand that part. So now what we are discussing here in terms of precedence, your and has a higher precedence from or, and not has higher precedence of anything. Like you first, if there is a not, you would perform it first and then or. Now each part of the right hand side of the equation is called a term. Then that means in this case x and y bar is a term and z is another term. In fact, inside this term x and y bar, x is a term and thus y bar is another term. Okay, so term is a individual components in the Boolean expression. Later, we'll see a function has two type of representation. One representation we are seeing here in terms of Boolean algebraic expression. Okay, in terms of variable names is complement, uncomplement form, connected them with the and or operations and so on and so forth. We can have another representation of a function which called a truth table. Okay, we'll see that. Just to make sure you understand, they convey the same thing basically, like a function, a Boolean function. Okay, either you are representing a function in terms of truth table where you are we'll see that we'll describe inside the truth table in terms of variable values combination and what is the outcome of that function from that combination, that is explicitly said in the truth table. Whereas the other form to represent a function is a Boolean expression. Okay, they're the same, truth table and Boolean expression. Okay, so here it is what I'm trying to say is that a function, let's say this function x and y bar or z. Okay, now this function can be represented, instead of writing a Boolean expression, can be also expressed in terms of a truth table, where we are explicitly defining different all possible combinations of x, y, and z. And this is easy because for the Boolean algebra, especially with the less number of variable involved in that function, that we can explicitly represent all the combinations of such variables, because like I have 3 variables and each variable can assume either value 0 or 1. That means I have only 2 to the power 3 combination, total 8 different combination that I can make out of these whole values of the Boolean system. Okay, so so we explicitly write down those value combinations of different x, y, and different variables in this function, which is x, y, z. So we'll have total 8 rows there, because there are 3 variables. 2 to the power 3 is 8. And we write down the possible outcome of the function. Okay. Here, don't think this way. Okay, we are kind of replacing the values of these variables and evaluating that expression, and to coming up with these values in this column of f, x, y, z. Don't think in that way. Okay, so what you need to see is that my function is defined in terms of truth table, which says that, okay, for different combination of its variable, different value combination of its variable, what is my function evaluate to be? What is my outcome of the function? That's all it is indicating. Now you can construct given. Now the point is, given this expression, like a function represented as a Boolean expression, you can construct a truth table form of the function. Means this same function represented as a truth table. You can do that, where you will replace these each individual values. Like you take each of this row, take individual values of this variable, replace that in the Boolean expression, perform the Boolean operations, and whatever outcomes you write down in the column of f, x, y, z in the truth table. For example, let's take 0, 1, 0. Okay, so 0 and 1 bar, or 0, which is basically 0 and 1 bar is 0, 0 and 0 is 0, or 0, which is 0. So 0, 1, 0 is 0. Let's take 1, 0, 1, right? Another example, 1, 0, 1. So what is, if you have to construct a truth table given this expression, then what you will do? 1, 0, 1, 1, x is 1, y is 0, 0 bar is 1, so 1 and 1 is 1, or 1, z is 1, so 1 or 1 is 1. So that becomes your function outcome. So this is like converting a function represented as a Boolean expression into the function represented as a truth table. How about the other way? Like, given a truth table, can I come back to this Boolean expression? Okay. Now this is the main topic of digital logic design. Okay. In digital logic design, we start with a truth table and try to find out what is the corresponding Boolean expression of the function. So we start with a truth table representation of a Boolean function, and from that we try to convert into a Boolean expression form of the function. Now why we want to do that? Now from a truth table, once we come with an Boolean expression format, like for this example here, so we have x and y bar or z, then just for time being, just take as granted that there are electronic component which can perform AND operation between two Boolean variables, inversion operation on one Boolean variable, and OR operation between two Boolean variable, or term if you want to call their term. So there are electronic component available to perform AND, NOT, OR. Okay, that means from a truth table, if you can come up with a corresponding Boolean expression, then you can construct those, you can really pick up those digital electronic component, like one AND component, another invert component, another OR component, and combine them to make this function fx f, x, y, z. However, please note this translation from a truth table into corresponding Boolean function is not trivial. It needs some strategy to kind of do that conversion, whereas the other way is kind of trivial, like you given a Boolean expression, how you construct a truth table, pretty trivial, we just explained it a few minutes back. But conversion from a truth table into a Boolean expression is not trivial, and we'll learn in the next lecture how we can do it. However, let's move forward with our review from our Math 42. So in Math 42, we have done some study on this basic Boolean function and its characteristics like and, or, and not. Now we can actually represent in terms of also truth table, right? So this is a basic AND gate truth table where output of this function AND is 1, or if only these related variables are both true or both 1. Everything else is 0. Or is just a different operation than AND, where I have 0 as outcome if both of my related variables are 0. Otherwise it's 1. And inversion is easy, like if my related variables value is 0, outcome is 1. If the related variables value is 1, outcome is 0. Now let's talk about two definitions in the Boolean algebra world. One is called dual of a given function, and another is a complement of given function, and we'll be discussing in terms of its corresponding Boolean expression representation of function. So dual of a Boolean function is obtained by replacing an AND, that is dot, right, with a OR, which is represented as a plus, and plus with a dot, okay, in the original function. And if any function involves a constant value like 0 or 1, we interchange them too. So if the function contains a constant value of 0, we change it to 1 in the dual form, and if that's 1, we change it to 0. For example, f(x,y,z), let's say it's a function xy or x bar z or yz. Okay, so here notice that I haven't mentioned this AND explicitly. So they're kind of, and also I haven't written that dot explicitly. So it's something like a normal algebra you do. Like if you do a multiplication of two normal algebraic variable a and b, so you make an a dot b. That's the usual thing to do. And we often actually drop that dot and write it as a ab, and we kind of, that dot become invisible, and we all assume the dot is there. So it's the same case here. For the dot, which is AND operation for Boolean algebra, we can drop it in the expression, and we all assume it is there in terms of this. When I write down xy, we really mean is x dot y or x and y. Okay. So, and when we say also, it becomes like xy or x bar z or yz. So that's kind of make it easy to say that expression kind of thing. Anyway. So given that dual of the f, so I need to change each dot to plus and each plus to dot. So and if there is 0 and 1, we need to interchange them, but this expression doesn't involve this constant value 0 or 1. So our dual form of this xyz would be x or y and x bar or z and y or z. We will be not dealing with dual like very often in our digital circuit and design and digital logic related topics, but it is kind of FYI kind of stuff for information. That is definition of a dual. But what we'll be using very often is the complement. Okay, so we very like understand what do you mean by a complement, especially in terms of Boolean function, complement of a Boolean function. It is very similar to dual. Okay, so function is obtained by changing 1 to 0s and 0 to 1, similar to what in dual, and also we change dot to plus and plus to dot. Okay, that's also like dual. However, unlike dual, what we do, variables are also complemented. So if there is an x bar involved, we change it to x. If there is an y involved, we change it to y bar. So we kind of complement, variables are complement together. Okay. For example, if x, y, z, let's say it is x bar, y, z bar, or x bar, y bar, z, then a complement of the function, which we denote as a f bar xyz. So in the left hand side, that is a complement of the function, and we complement each of the term in the right hand side as well, and interchange dot with plus and plus with dot. So this becomes like x or y bar. Note that y is uncomplemented on my original function, so we make it complemented, or z. Note that z was complemented in my original function, we uncomplement it basically in the complemented function. So this become x or y bar or z, and similarly x or y or z bar. So that's my complement function definition.